Hi there. Welcome back. This is going to be a Physics 212 prep video. Suppose it could also be used for prep for Physics 112 as well. So today what I wanted to talk about was specifically charge and some of the effects of electric charge. So this whole class is going to be about electromagnetism. And the first few sections are going to be particularly about a field called electrostatics, which focuses on just electric fields caused by charges, and how electric fields affect charges, and specifically charges that aren't moving. And so we'll take a look at a few ideas that we'll start with. So to start out, we're going to take a look at the idea of electric charge, which you've probably experienced quite a bit of in life. This quantity is scalar. It's a scalar that can be both positive and negative, and it's denoted by little q, usually for a smaller charge, and big Q for like the whole charge of a system. Once again, it can be positive or negative, and it's special because like charges repel, and different charges or dissimilar charges attract. And so let's look at that. So positive will repel positive, negative will repel negative, positive will attract negative, and negative will attract positive. So these are all the possible configurations. There's 4 permutations there. And the units that we use for electric charge are coulombs, named after Charles Augustin de Coulomb. And 1 coulomb is now defined, of course, they had no idea what electrons were in Coulomb's time, but we've decided to define 1 coulomb as 6.24 times 10 to the 18 electrons. So I mean, that's quite a bit of charge, and I think you'll find that a coulomb is quite a lot of charge. So we usually won't be dealing with a full coulomb. That doesn't show up very often. All right, so let's start with Coulomb's force law. Coulomb's force law states that the magnitude of the electric force between 2 charged particles is equal to a constant times the magnitude of the first charge times the magnitude of the second charge divided by the shortest distance between the 2 charges squared. All right, so K sub E is Coulomb's constant. It's approximately 8.99 times 10 to the 9 Newton meters squared per Coulomb squared. So let's start and take a look at this example 1. We have charge 1 over here, Q sub 1. It's got a charge of 1 times 10 to the minus 6 coulombs. Then we have charge 2 over here with 2 times 10 to the minus 6 coulombs. And the distance between them is 1 meter. And so we're going to find the magnitude of the electric force first, and then we'll just draw the direction, or we'll figure out the direction. So if I want to find the magnitude of the electric force between these 2 charged particles, I would plug in Coulomb's constant, 8.99 times 10 to the 9. Then charge 1 is 1 times 10 to the minus 6. Or I should say the absolute value of charge 1 is 1 times 10 to the minus 6. Absolute value of charge 2 is 2 times 10 to the minus 6. And the distance between them, the shortest Euclidean distance between them, is 1 meter. And so I'll square that distance. It just gives us 1. And I worked this out ahead of time. What you end up getting is that the force between the 2 charges is approximately 0.018 newtons. All right, so a little bit of a force there. We don't really know what the mass of these charges are, and that's really unimportant at this point because remember, we're doing statics, electrostatics. So these charges, we're pretending like we've nailed them to a board. They're not allowed to move. Now, obviously, a force is going to create an acceleration, but we are applying a sufficient normal force to these charges to keep them from spreading apart in this case. Because we have 2 positive charges, So they're like charges, so they will repel. So what we'll do for that is we'll draw the radius between the two particles, or the distance between the two particles. And the forces between these two particles will always lie on this line, what's called collinear to the line. So they're parallel and they're on top of the line. In this case, we'll say there's a force that's pushing Q2 this way, although we're not allowing it to move. There's a force that's attempting to push Q1 this way. And thanks to Newton's third law, we know that these forces are equal and opposite. And there's a little index system that we're going to use. We're going to call this F sub 1, 2. That indicates that this is the force that charge 1 is applying on charge 2. And so, we've found that it's about 0.018 newtons. And, we could go ahead and say, that this is the x direction. And so we could go ahead and say 0.018 newtons in the I hat direction for the force that 1 applies on 2. And then over here, the force that 2 applies on 1 is of equal magnitude, right? Equal and opposite according to Newton's law. So it's negative 0.018 newtons in the I hat direction because it's pointing in the opposite direction of the x direction. So this is how we would write those electric forces as vectors. Whereas when we calculated using this equation up here, we just found the magnitude of the force, and then we were able to figure out which direction they were going to point. All right, example 2 is nice because the the absolute values of the charges haven't changed. And so we're going to end up with that same magnitude of the electric force, 0.018 newtons. The only difference now is that this charge over here is negative, this one's positive. So those are dissimilar charges and therefore are going to attract. And so once again, we draw the shortest Euclidean distance between these two charges, but now they are attracting. So now we have the force that 1 applies on 2 is pointing in the negative I hat direction. And the force that 2 is applying on 1 is pointed in the positive x hat direction. So this first section is, it's not so bad. This equation, it's pretty plug and chug. So really at this point, just practice some of these problems. Probably a few will suffice. The indices system is really nice. Right now, we're just dealing with 2 charges at a time. In the future, we'll be doing 3 or 4 charges and figuring out the net force on, say, one of the particles, one of the charges. And to do that, it's just like we did in 211 or 111. We just figure out all the forces acting on a particle, and then we take the vectorial sum of all those different forces, and that'll give us our net force. So pretty similar stuff. One thing I wanted to point out is that you recall that at the end of last semester, we talked about Newton's universal gravitation law. States that the force due to gravity, I'll go ahead and say the magnitude of the force due to gravity, is equal to a constant called big G times the mass of object 1 times the mass of object 2 divided by the shortest distance between the two squared. So I just want you to notice how very similar this universal gravitational force is to Coulomb's force law. They're almost identical. The only difference is that we only know of positive masses, so we don't have to put the absolute value signs in for masses. So I will be having a video soon discussing what's up with this inverse square relation. In other words, you'll notice that if we were to double the distance between 2 charged bodies, we would divide the force between them by 4. So in other words, the square of 2 is 4. If I were to triple the distance between 2 charged bodies, I would 1/9 the force between the two. And that's the same for gravity. And just a little teaser on that. So this is one way to write Coulomb's force law, the way I have it written up here. There's another way to write it, which I will put down here. And that says absolute value of Q1 times absolute value of Q2 divided by 4 pi times a constant called epsilon naught, or epsilon 0, and then of course times the radius squared. So if both of these equations are valid, what that tells us is that the Coulomb constant must be equal to 1 over 4 pi epsilon sub naught. And so epsilon sub naught is called the permittivity of free space. And it is essentially how much, like a vacuum, like imagine space, there's nothing in it, it's free space. And this constant kind of tells you how electric fields will behave in that kind of a material. For example, you could have an epsilon for glass, or for different kinds of glasses, or epsilon for cardboard, because electric fields will behave differently in different materials. And it just so happens that epsilon sub naught, of course, is going to be the inverse, or well, not quite, but it's well, it's 8.85 times 10 to the, I believe, minus 12 Coulomb squared per Newton divided by meter squared. So, all right, one thing I want you to think about before next video is, do you recognize 4 pi r? Where does 4 pi r come from? Think about that a little bit. Where have we seen that before in math and physics? Anyways, I hope this video was useful to help you start getting going with Physics 212. This is chapter 22, I believe. All right, have a great day and see you next time.